My favourite shape is one you've probably never even heard of. The Metaball. These are all metaballs. Metaballs can be convex, concave, round, spiky, or even unconnected. But if all of these are metaballs, and I could swear that one of those shapes looked awfully like a circle, what on earth is a metaball? What's a metaball? Put simply, a metaball is the shape you get when you smush multiple balls together. Suppose, for example, that we want to smush these two balls together. Two simple ways of doing this would be to either A, increase the size of each circle until they touch, or kiss is the nomenclature often used, or B, to draw a bridge between the two circles. But both of these are a bit unsatisfying. If we blow up the circles until they touch, we not only end up with a shape that's unsatisfyingly spiky, but the circles themselves have gotten noticeably larger. This doesn't feel quite right. On the other hand, if we draw a bridge between the two circles, this shape is called the convex hull of the set of circles, we get another sort of unsatisfying shape. For lack of a better word, it just doesn't feel very smushy. Maybe we could fix that by just making the entire shape an ellipse, but that doesn't feel very satisfying either. Alternatively, we can take a different approach. What if we add in the points that are moderately close to the centre of both circles? Then this point would be present in our new shape, but this one wouldn't be. This gives us a new shape, the metaball. The maths. Okay, we've got the intuition out of the way, but let's get into the nitty-gritty. The mathematics. How do we precisely define a metaball? A good place to start would be by looking at the distance between a point and the centre of both circles. We can't use the sum of a point's distance from the circle centres, since that can only cut away points from the two circles, instead of adding points between them. Instead, we can add together the inverse distance between our point and the centre of our two circles. To see why this is the case, let's look at the equation for a circle. A circle is defined as the set of all points such that the distance between our point and the circle's centre is less than a threshold. This threshold is called the circle's radius, r. But we can flip this equation. Instead of having distance smaller than or equal to r, we can have 1 over distance above or equal to 1 over r. Then to construct our metaball, we just write 1 over the distance between our point and C1 plus 1 over the distance between our point and C2 is above or equal to 1 on r. Okay, that's great. But how do we get those weird spiky metaballs I was showing earlier? Well, you get those by altering your distance function. Instead of using the typical distance function of the distance between a and b being equal to a.x minus b.x squared plus a.y minus b.y squared, all square rooted, we can vary the power. We can instead write the distance between a and b is equal to the absolute value of a.x minus b.x to the power of p, plus the absolute value of a.y minus b.y to the power of p, all peep-rooted. We just added the absolute value to deal with some annoying negative signs that can blow up the equation. At very small values of p, you get these star-like shapes, and at large values of p, you get squircles. Two things are worth noting here. A, if p is smaller than 1, then you no longer have something called a norm. The mathematics behind this concept are a bit complicated for this video, although I recommend you look up something called metric spaces if you're interested. But this means that our metaballs are no longer necessarily connected. We can make shapes like this, that have more than one disconnected piece per centre. B. For all values of p that aren't equal to 2, we lose rotational symmetry. This means that our shape will vary by the angle between our two centres. This isn't the case for p equals 2, and that's unique. If you're able to work around those limitations, though, you can get some very interesting results. Thanks for watching my video. If you're interested in Metaball art, make sure to click my Metaball playlist linked below. And if you've made anything with Metaballs, make sure to leave a comment so I can take a look. I would love to see the work of other artists. If anyone is interested in the nitty-gritty details of implementation, plus some technical aspects of coding Metaballs in 3 dimensions and beyond, I can make a follow-up video later.